Okay, we're going to get started. This talk is on how container schedulers and software-defined storage will change the cloud. Our speaker is David Van Thenen. He's a software engineer with Dell EMC. And in a nutshell, this talk is about having HA containers in the cloud, high availability in the cloud, an environment where you have apps which can self-repair themselves. So without further ado, I give you David.
All right, thanks guys. Thanks for showing up. So yeah, we're going to talk about container schedulers, we're going to talk about software-defined storage, and we're going to talk about when you take those two things up into the cloud, what does that mean for you? So I, already in the intro, I work for Dell EMC, and I work for the code team, which is a group that specializes in open source software. We do various storage integrations with a container in the container space, so everything from Docker, Mesos, Kubernetes. And prior to this, I used to work in the backup and recovery space for virtualized environments, like VMware in particular, so doing VMware backup. Yeah, so my name's there, code by Dell EMC, Twitter handle, and my blog, so in case you guys want to check it out. So the agenda. So we're going to talk about, I want to do kind of a really quick review about software-defined storage and what that really means, because if you go looking on the internet, there's like 100 different definitions of what that actually is. So I kind of just want to touch on some things that are common among some of those definitions. And then I want to talk about container schedulers, and I'm going to give a really kind of a high level, and then I'm going to kind of go into the weeds a little bit to talk about some of the offerings that are available in container schedulers today. And then we're going to take a look at what happens when you combine these two, right? We take software-defined storage, you take container schedulers, what types of things can you do, when you tie these two things together? And then ultimately the whole idea of the talk is what happens when you take this stuff into the cloud. And today apparently I'm crazy enough, I'm going to do the demo live, so hopefully the demo powers that be are going to smile on me and it's all going to work. So, software-defined storage. So yeah, like I said, many definitions, but I think kind of like the two main things that most people agree on is that software-defined storage usually serves as an abstraction layer on top of the underlying storage. So there's usually some form of, you've seen in the volume source, we have the idea of logical volumes and the idea of physical volumes, and it's kind of that abstraction layer that exists between physical and what's offered up to the end user. And also software-defined storage, the common kind of agreement is that it provides a programmatic mechanism, right, to provision storage, right? So if you don't want to, if you need to allocate more storage or do an operation, a maintenance operation, or do some sort of operation on your underlying software-defined storage platform, that there are APIs available to do that. So like a couple examples of what software-defined storage looks like. So NFS is a very simple example of that. And then kind of on the further extreme, like VMware vSAN. I don't know how many VMware users or people who are familiar with VMware, but vSAN is like a good example of software-defined storage. So what makes software-defined storage unique? So I kind of already listed some of that stuff out, but I kind of want to dive into that a little bit more. So operationally, you manage provisioning of that storage and the data, like how that data is presented to the end user, independent of the underlying hardware. So I kind of already mentioned that, but I really want to make that point like really, really clear. Then the second thing is physically, like on the physical side, right? You have a abstraction layer that kind of breaks apart what's offered up to the end user and what's actually attached to those systems, right? So as an example of NFS, you could have physical disks that are just normal rotating media, but when you have NFS and you expose it up to the end user, it's just an NFS share, right? And policy. So this is kind of a new thing that we're just going to throw in there. So policy. With software-defined storage, there's usually an automation of policy both driven by the external user and also to the internal storage platform. So what does that mean? So say I'm a user and I want some storage, and you can classify certain storage into like buckets, like gold, silver, bronze, right? Maybe gold is your SSDs, and bronze is kind of like your rotating disk, right? So there's this policy that's associated with the varying levels of storage that are available. And something that's also different, right, because we're talking about software and we're not talking about like large racks with rotating disks in them. Day two operations, like what happens when you need to perform maintenance on these storage systems. It's inherently different, right, because you're not dealing, I mean, ultimately on, diving into the details, you still have disks that are out there, but because it's all software based, how you perform maintenance is inherently different than doing a rebuild on the RAID array, right? So just kind of because I'm a very visual type of person, so this is effectively NFS. This is what NFS looks like. We have a host, we have two physical disks there at the bottom, and on top of that, those two physical disks, which might be combined as an LVM group or whatnot, you have that software-defined storage layer sitting on top of that, right? Which is just, if you were to put up a NFS server, right, you would do like an apt-get install NFS or yum install NFS, right? And from that, you expose effectively a volume or some entry point into this NFS server, which gets mounted onto other systems, and that's how the end user consumes that storage. So, since I had talked about vSAN, so this is on the far extreme. This is a slightly more complex example of software-defined storage. So, in the VMware vSAN world, you need a minimum of 3 nodes, and you have rotating disks, which is there at the bottom, and then you have SSDs, which are kind of sitting above that act as a caching layer or write cache layer, so that the rotating disks, when you want to, write to this particular vSAN, you store all the writes there and give the rotating disks enough time to catch up so that you can persist it into the physical rotating medium right there. And so that vSAN layer, what it does is it takes all 3 of those servers, takes all that storage and makes it look like a globally accessible pool that straddles across all 3 of those hosts. And when you provision vSAN volumes, it comes out of that globally accessible pool and you present them to your host. So a slightly more complex example of what a software-defined storage network looks like. So one thing I kind of wanted to really kind of highlight is what makes, the reason why I picked NFS and vSAN, what makes NFS and vSAN special, right? And it's kind of the idea is that they're all software-based storage platforms, right? You don't need any kind of specialized hardware, a special purpose-built appliance, some kind of storage array, some kind of rack with the storage controller in it. So it's literally software that you could download, right? So in the case of NFS, you can do an apt-get and install NFS. And in the case of VMware, it's slightly more complicated, but you install in your ESX installation media. If you have the licensing for it, you don't need any special hardware. You just have your systems with your SSDs and your rotating disks, and you can create yourself a vSAN array. So that's kind of just a very high-level overview of storage. So I kind of wanted to jump through that very quickly because just to kind of level set on the idea of software-defined storage. So next, we're going to take a look at container schedulers. So who here has used Mesos, Swarm, or Kubernetes? Show of hands. Okay, so a few people. So I'm going to kind of define go over what a container scheduler is, and for the people who haven't used any of those. So a scheduler effectively takes a container and it places that container in a fair and efficient placement within your compute cluster. And you typically want to have the placement of that workload adhere to a certain set of constraints. So for example, if you want to deploy 3 instances of this particular container, it makes a lot of sense that you don't want to have all 3 of those instances of that container appear on and start on that same piece of compute, right? So you would want, ideally, if you want some sort of high availability, you'd take those 3 instances and say, hey, I want you to make sure that when you start up these containers, to put them on 3 different pieces of compute, right? 3 different compute nodes. So that when one goes down, right, you have the ability to not lose your entire application. And schedulers also have this idea that you can quickly and deterministically dispatch your jobs. So what I mean by that is, if you have a particular application that you have where you have 10 instances of your container installed and running, and you want to scale that application up to like 100 or 1,000 instances, you want to know how long that's going to take so that your application's fully scaled out and fully available, right? And also, you want to make sure that your container scheduler is robust and tolerates errors, right? So anytime you're going to deploy anything into production, if you have a particular piece of compute, go offline because of a hardware failure, you want to make sure that those containers get torn down on that host, or well, in that case, they're just lost, but those containers will get moved over to a different piece of compute. Your application will come back up, and then it's available again. So, when I say containers, like what types of containers, right? So containers, I'm talking about in the sense of Docker. So Docker, you see here at the conference this past couple of days talking about Docker. Mesos is also another containerizer provider. So Apache Mesos is an open source project, and it does container scheduling. And funny enough, Mesos also supports Docker as well. And then there's also Rocket. So, got the guys at CoreOS in their booth out there, so you can talk and find out more information from those guys. So those are the types of containers that I'm talking about. And when you schedule work, right, the container scheduler is also effectively also a cluster manager. If you have your cluster and you have your certain compute nodes that are running, if you have a failure on that node, you want to make sure that the tasks get moved over to a different node. And so that's exactly what the definition of a cluster manager is. And when those workloads get placed on your pieces of compute, you want to make sure that those tasks are placed based on resources. So as an example, Apache Mesos, when you want to define a particular job or task or an application that you want to run within your cluster, like the three criteria that are most common with Mesos is, this container requires X number of CPUs, it requires like 2 gigabytes of memory, and it requires this much disk, right? So tasks are launched on these pieces of compute based on the resources that are available in your cluster. And then there are also operational constraints. So if you're going to launch a container, I've already used the example of, if I'm going to launch 3 instances, I want to make sure those 3 instances are on 3 different pieces of compute. Now, here's like another example of that, is if instead of on 3 different pieces of compute, maybe this particular application needs a kind of a higher level of high availability, and maybe instead of saying, I'm going to put these 3 instances on different compute, maybe it's, I want to put these 3 instances in a completely different rack. So you can do things like that with container schedulers. So a lot of the modern container schedulers today, most of them have some pretty cool features, and one of them is the ability to create your own custom scheduler. So if you have a particular application or workload where there's some intricacies about that application that the default scheduler cannot provide, you have the ability to create your own scheduler. And you effectively take the resources that are available, find out what placement is best for your particular application, and that custom scheduler then decides where it should place those container workloads, right, where your application is going to land. So like some examples of what you could customize is like the runtime, availability, going back to having your application installed in multiple racks. Maybe you need to have 3 instances in each, or 3 instances in each data center row, right? And then you have, maybe this application has some built-in fault tolerance where it's doing real-time fault tolerance, and when you lose one node, the next node can pick up and continue on. And maybe you have a particular application that does some like graphics processing, right? And you have within your cluster, you have GPUs that are highly effective at, processing graphics, movies, doing audio, video decoding, and you want your workloads to land on those nodes because they're better suited to process that particular application. You have the ability to customize that. So got the cool little guy here with the different shirts and stuff like that. Customization's good. So I kind of wanted to take a look at one particular container scheduler because there's a lot of them out there. Oddly enough, it's the one I'm most familiar with. So kind of want to talk about Apache Mesos. So like I said, it is a container scheduler, right? And it's an open source project. It supports Docker workloads, and then Mesos has their own containerizer that's kind of a lighter weight version of a container. It does container placement, or it deploys your containers based on CPU, memory, and disk, right, is the three kind of criteria that I said. And it also provides you to do user-defined constraints. So you place these two in this particular rack and whatnot. I have a list of logos here. So Apache Mesos isn't a new thing. It's been around for quite some time. It's in production, and it's all these companies have some Apache Mesos installation. And so if you use any of these services today, as an end user, you've been using Mesos, right? Because all these companies have these installations, at scale at like thousands of nodes. So why did I pick Apache Mesos to talk about? So Apache Mesos has this cool idea where they have a technology called Mesos frameworks, where it allows you to customize placements of your Docker containers or your Mesos containers based on what your application needs. And the way they implement this, and now we're kind of diving into the weeds about some of the details of how a framework operates, but the framework implements two things. It implements a scheduler, and then it implements an executor. So the scheduler is the one that gets resource offers to it, and then that scheduler, this custom scheduler for your application, then says, hey, I'm going to deploy my application to this node in the form of this thing called an executor, which is effectively a container that is going to use some CPU, memory, and disk, and then it's also going to deploy your application. And in the Mesos world, they call this the offer accept model. So kind of a cool little animation, offer up memory, you get an application back that's using X amount of memory. Anything that you're not using gets returned back to the pool. And this particular framework is custom, if you created this framework for your application, this is a custom framework for your application. So you could have many applications running in Mesos where it may have its own framework, or maybe it's the default framework or the default mechanism for scheduling is sufficient enough and you can just live with that. But the cool thing is it allows you to completely customize how your application gets deployed in this environment. So that process, what I had just described, this is kind of the cool little diagram for it. You guys can I'm going to post the slides later. It's probably up on SCaLE's website already. This just kind of goes into a little more detail. Resources get offered up to the control plane. Framework gets the resources, decides to deploy an application, sends it down to compute. 1, 2, 3, 4. So now we kind of talked about software-defined storage, and we talked about container schedulers. And there's a lot of information that's I've already talked about. Now we're going to talk about what happens when we take these two kind of independent pieces and kind of bring them together. So I kind of had this idea back in September 2016 that said, hey, what happens if I create a software-defined storage framework for Mesos? Like, what does that mean? So I kind of went off and I said, hey, I'm going to pick a particular piece of software-defined storage. In this case, I use SCaLE.io. And I combine that with the technology of Mesos frameworks. And it kind of opened the idea of like a whole kind of way of thinking about applications and how they get deployed and how you really ultimately consume them. And so it was released in September 2016. We're kind of now on version 0.3.1. It's open source, so you have the GitHub link there. You can go ahead and take a look at the code and, you know, contribute or open issues if you find any. But it's this idea of combining two different things, right? That when you combine them together, it makes it's better together, right? So I got the Oreo cookie and the milk. I don't know anybody who hates that combination. So, as I said, SCaLE.io is a software-defined storage platform, and I'm just going to have one slide about it because really, ultimately, this can be done with any software-based storage platform, but I chose SCaLE.io to use in particular. So it is a software-based storage platform. It has scale-out block storage. So what's cool about SCaLE.io is that if you start to, you know, if you need more capacity in your software-based storage platform, you can either add more disks to the SCaLE.io nodes that are there, or you could add more nodes. And the cool thing about SCaLE.io is that it linearly scales. So as you have more nodes, the number of IOPS and performance grows along with it. And that kind of gets back to this whole idea of having an elastic architecture, right? So add drives, add more nodes, and if a particular node goes down, SCaLE.io, because it's a software-based storage platform, will go ahead and rebalance itself. So that's kind of why I had hinted earlier on that when you have failure or when you have changes in your software-based storage platform, the maintenance operations change. And in this case, there's nothing that the end user really needs to do, right? It basically fixes itself when you have a particular node failure. And then the other cool thing is because this is a software-based storage platform and it doesn't require any kind of specialized hardware, you can download SCaLE.io as RPMs and deb files and install them anywhere. It's infrastructure agnostic. So if you wanted to install this locally, like, you know, on physical bare metal, go ahead. If you want to install this on virtual machines, go for it. Or if you want to take it into the cloud, like in AWS or GCE or Golden. And you can go ahead, download it, and give it a try. Yeah, that's kind of all I'm just going to say about that. So what does this software-defined storage framework really mean? So if kind of the idea of this framework is to install an application, right? Find the best place and the best mechanism to install this application such that it performs in the most optimal way it possibly can. And if you have a framework that installs a software-defined storage platform, it manages the installation and the configuration of that platform. So effectively what you do is you deploy the framework on all of your pieces of compute. It installs a software-based storage platform. And if you do that from day one, as soon as you stand up your Mesos cluster in this case, you'd have persistent storage access that's native on every piece of your compute from day one without having to know anything about SCaLE.io. So that's kind of the cool idea. And because SCaLE.io is a software-based storage platform, it provides global access to external storage so that if you need to provision a volume from any one of these nodes, you can go ahead and create this volume, and no matter where your container workload hits and lands on a piece of compute, because it exists on every node, you're basically guaranteed access to these volumes. And because it is all software-based, like I said, if you had a node failure and you need to rebalance the data that exists in this software-based storage platform, there's no storage array, right? It all exists on software. It's all using the local disks that are attached to your individual pieces of compute to make it look like such that it's a huge globally accessible pool of storage. And because it's infrastructure agnostic, you can literally deploy this thing like anywhere. So why is that important? Why do we even care about that? So if we take a look at containers today, if you look at a lot of the workloads that are being run in container form, many of those containers are long-running, persistent applications. right? They have applications that require state, that require data to be saved somewhere. Even something as simple as configuration is state. So if you take a look at, I have on the, I guess it's your right-hand side. If you look at the right-hand side, this is a snapshot of Docker Hub. So these are the top 12 applications that you see in Docker Hub. If you take a look at that, the top 7 of those 12 are actually persistent applications. So if we take a look, it's kind of hard to see, but you know, you have Mongo, you have MySQL, you have Postgres, you have Elasticsearch, and even WordPress to a certain degree, right? You write an article, that article gets created and saved somewhere, right? So these are persistent applications that are running in containers today. Oops, wrong way. So if I do have these persistent applications, like Postgres as an example, right? And I start up Postgres and I need to save that data. If I don't save that data somewhere else, when I take Postgres down and I shut Postgres down, the container dies, where does all my database data go, right? So a lot of the container schedulers, what they decided to do was, hey, I recognize that this thing's landing on some form of compute. This piece of compute has some sort of access to local disks. I will just take that data, expose a folder or a piece of that local disk to that container, and you can save the data. You can save your data there. So you bring up Postgres, you start writing to this specially carved out section of data or this directory where you can store your Postgres data to, which just exists on your local disk on that particular piece of compute, and you're all happy. You've stopped your Postgres database that lives in this container, bring it back up on that same node, and it recognizes that that mount's there, and you have your data, no data loss. Now the problem is what happens when you kill that node? What happens if that node, for whatever reason, has a hardware failure, goes out for maintenance, or has some sort of issue where you can't get at that local disk anymore? So if you're trying to do something like that and you don't have any form of high availability, is effectively what we're talking about, being able to take that workload, that container, move it from one host to the next, and have your data, you're probably not going to run that in production because, if all of a sudden the finance database is gone and you're trying to recover that, that's probably not a good story for, your higher ups and your bosses, right? So what's the solution to that problem? So, like I kind of already said, you want to make sure that that data lives external to that piece of compute. And that's kind of where SCaLE.io comes in, right? So you have the software-defined storage platform that's where if you need a volume that's globally accessible on every piece of your compute, if you need to bring up that container on a different node, because you have access to that storage platform, you can reattach the volume that it was using on a different node so that you have all your data. And that's kind of like the value add of why, like software-defined storage or software-based storage platforms, why it means something and why it's important for containers in production. So this framework, I'm just going to kind of mention a couple things right here. So this framework installs your storage platform, but there's nothing there really to hook up and provision the storage, right? So the framework installs the storage platform, you have your containers, you can run them, but how do you hook up your container to provision a volume from the storage software-based storage platform? Say that 10 times fast. How you take that software-based storage volume and how you connect the two, right? How you take that volume and connect it to the container. So the framework also leverages 2 other open source projects. The first one is called RexRay. I'm using it special purpose built for what I'm trying to do, but RexRay, if in the grand larger scheme of things, it's a vendor agnostic orchestration engine that supports many different storage platform backends. So a fancy way of saying is if I'm in AWS and I need to provision an EBS volume for a container or for practically anything, like an application that's running on an EC2 instance, I can use RexRay to create that EBS volume, attach it, and mount it to wherever I need. And in this case, I'm using it I'm using RexRay to create the volume and attach it, but attach it to that container instance so that when I need to save data, I'm saving data to this software-based storage platform in the volume that's created there. And another one is Mesos module DVDI. So RexRay is effectively a Docker volume driver plugin. So that kind of satisfies like use cases for Docker. And for Mesos module DVDI, it's essentially a library that hooks, it actually hooks up to RexRay. So it just is one level of indirection where it calls RexRay to create volumes and attach volumes to non-Docker workloads in Mesos. So effectively, if you're running a Mesos container, if you want external storage for that particular application, it will go ahead and provision the volume and attach it to that non-Docker workload. And both of these projects are open source. Like I said, RexRay, I'm using it for something very specific, but it supports AWS, GCE, DigitalOcean, Rackspace, VirtualBox if you want to just do local testing, and then because we are Dell EMC, it supports a lot of Dell EMC storage arrays. So we now have the ability to create volumes, move them around in our Mesos cluster. And so what does this really mean for your application, right? If you have a node failure in your Mesos cluster, you effectively have high availability for your applications. That workload, whether it's Docker or Mesos based, that container will move from one node to the other. That software-based storage platform volume will follow that workload to whatever piece of compute that it lands on, and it'll have access to its data. But kind of a little bit more important than that, why is this idea of this framework like a good thing? And kind of two big things right here is that one, this framework manages your software-based storage platform, which means that it's the one that's dealing with all the APIs for the storage platform, and it's also dealing with all the changes for your container scheduler. So it's making the API calls to Mesos so that you don't have to deal with that stuff, and it's also making the API calls to install and configure your storage platform. And in the end, to you, as the end user, you really don't care, right? So you deploy this framework, you get a software-defined storage platform, which you really don't have to know how or why, what's required. There's actually 3 metadata nodes that get installed so that they can do arbitration when a frame drops, and but as an end user, you really don't care, right? You just want to have this storage platform available for your applications and provision volumes from it, and that's effectively what this framework does. And then that in turn gives your containers that whole production level of readiness, so you can put it into production, and should something go wrong, everything's golden. So I kind of have this story that I've been kind of building up, and the last section of this is what happens when I take this into the cloud. So if I take this into like AWS, for example, because that's what I had implemented, what does this mean? So we kind of already talked that software-defined storage, by definition, has APIs. It has the ability to make API calls, manage them, do certain things like maintenance operations and whatnot, right? We all know that cloud is, one of the reasons why cloud is so awesome is that they themselves also have APIs, and, DevOps processes use those APIs to, stand up all these EC2 instances and whatnot. So, what makes all this stuff kind of work, and what's the whole crux of why all this stuff is important? It's all the APIs that are available, right? It's all these program interfaces that you can create these applications, manage your application, and manage the cloud. So if you have applications that have APIs where you can say, hey, I have this particular application, I can make API calls, and I can deploy and configure this thing, I can take a look at, make these API calls and monitor my application. I can actually determine the health of this particular application. And I can say, hey, if something starts to go south, like I have some sort of fault in my application, I might actually be able to do something about that now. And so the idea was, if you take the, you have an API where you can monitor your application, you can actually start to have your application go ahead and fix itself. And that's kind of, I have this cool picture from Short Circuit, Johnny 5 is alive. So this application starts to like pick up on its own and, start fixing its own problems, right? But kind of more importantly to that, if we have an application that can, determine that it's got a problem, it's got an issue, and then we see that since we're living in the cloud now, so in this example we're using AWS and we have our software-based storage platform and our Mesos cluster within the cloud, and we have AWS SDK bindings that are available in 10 languages, and we know that we can manipulate AWS using these APIs, you can actually have applications that can start changing their environment that they live in. And I thought that was kind of a cool idea. And so if you need to do some sort of maintenance operation or you need to do some sort of remediation, it's actually aware of the environment that it lives in. And I kind of, obviously this is a gross exaggeration, but you self-aware application Skynet kind of stuff, right? I only implemented a small piece, so it's not like we don't need to, start hunkering down and building bunkers or anything, but it's just a cool idea. And so, like I said, frameworks that can monitor themselves, self-remediate this software-based storage platform. So what I'm actually going to demo in a second here is this software-based storage platform has a storage pool that's starting to approach full. It identifies and sees that it has no more storage left, right? We're starting to consume all this storage. The application itself, the framework, identifies this particular problem. Since we're living in AWS, it goes ahead and creates the EBS volumes and adds those EBS volumes to the software-based storage platform, and we go from we're almost full to we're okay. And so that's what I'm actually going to demo here, and hopefully this works. So the slides will be available, the kind of more information about the configuration, all the open source software that's being used right now. I just want to kind of go over about what this looks like in the back end, because it happens very quickly, and that's actually a good thing for you as the end user, because the more the details and stuff that you see when the things are going back and forth and all this stuff, that means that you need to be aware of them. This whole process just starts with a simple curl command to install this software-based storage platform. I'm going to do that today, and hopefully it'll work. So we install this framework. Like I said, it's broken up into two components. The scheduler gets created. The nodes offer up their resources. The scheduler says, hey, I can use those resources, and I'm going to install this software-based storage platform, RexRay and Mesos module DVDI, right? Those are the two pieces of the two glue components that hooks the storage up to the container. And we're going to simulate like pumping a whole bunch of data into the storage platform. We're going to get a warning saying, hey, we need to seriously take a look at this because it's about to go south. We're going to make effectively the scheduler is going to say, hey, I'm going to make an API call to Amazon, provision volumes, attach them to this storage platform, and everything will be fine. So hopefully this works. This would be really bad if it didn't. All right. Let's see, I'm going to make this bigger, right? Tell me when you... Pretty scary. So maybe take you for a test drive for Mesos too. Just take a look at what we're looking at. So this is the Marathon UI. And this effectively, this is how you launch. Marathon is what you use on Mesos to launch an application. And the funny thing is that Marathon itself is a framework. Maybe this is too much information, but Marathon itself is a framework, and we're going to launch a framework using a framework. So anywho, so this is the UI that we're going to see, and we're going to come back to it a little bit because it's how we can take a look at the progress of this, our framework. And I copy this curl command here, and I'm just going to curl that to Marathon, so it's just effectively a Marathon API call to say, start the SCaLE framework. And that's a bunch of nonsense. Don't worry about it. Please work. Okay, so SCaLE scheduler. We're going to take a look at the user interface for this particular scheduler, or for this framework. So we have 3 nodes in AWS. These represent our compute nodes. So it's installing the SCaLE packages right now. It's creating the SCaLE cluster and initializing it. Please work. Takes a little bit of time because it's creating the cluster. It's taking the 3 nodes that are there. It's actually standing up the metadata instances. It's creating a 3-node high availability cluster. I have 3 180 gig disks in EBS that are attached to each node. Those disks are getting contributed to that storage platform. We're installing RexRay, which is one of the glue components that we need to provision volumes for your container. And since actually SCaLE is already up and running at this point because we're only just installing the glue, as RexRay is getting installed right here, we can already see that the capacity here, we already have some capacity that's available, right? And then after RexRay gets installed, we can see that SCaLE is running. So how cool is that? I curled a command. I didn't even know what was actually happening under the covers. But at this point, if I wanted to create a container like Postgres and I wanted to save the data into SCaLE, no matter what node it gets placed on, because SCaLE is running on every node, it will provision that volume, and you as an end user just think of it as a service because it's just running in the background and you didn't really need to do anything to start this. So that's pretty cool. So I have SCaLE, a software-based storage platform running on my Mesos cluster. I have some capacity, and I can see that because obviously it's new. I don't have any of that storage currently being used, so that's the %. And I created an arbitrary threshold. So as the SCaLE storage pool passes 90% capacity used, that is what's going to trigger the, oh my gosh, we need to allocate more storage to this platform. And so kind of to simulate that, I was planning on doing it so it would actually dump a whole bunch of data into it, but that took a little bit too long. So what I did was I created a little API call that says, fake like I'm going to dump that much data so that we don't have to sit here for the next 5 minutes. And yeah, I appreciate your guys' time, and that's not good. So I'm going to take, right, this represents the UI, right, where the UI for this particular framework, I made it so that the REST API call that I'm going to make is in this same exact web server here. I'm going to open Postman. Oh gosh, let's see here. So I'm going to open Postman here. I copied that URL where the REST API sits. The header here, normal JSON stuff. Effectively say, create this much fake data, right? This amount right here. And I'm going to call the API. Cross my fingers. Oh yeah. All right, so we can already see that the fake data is already there because it's not actually generating data. So fake data, used fake data is here. We're at 98% of used capacity, right? So we've passed that 90% threshold. Since we're in Amazon, so it's actually creating, kind of missed it. It happened a little too fast, but we're creating right here this last 1 terabyte volume. So we created 3 of them to represent each EBS volume that we're going to attach to each node to allocate more capacity to this storage platform. And hopefully, so it should be finished pretty soon. So now it says it's in use. So cross your fingers. Hopefully this works. So what we should see is we created 3 1 terabyte volumes. What was there before was only 3 180 gig volumes, or EBS volumes. So we're adding a whole bunch of storage to this pool. So we should see the capacity once the EBS volumes get added to the storage platform. The back-end capacity for the storage pool increased dramatically, right? Because we were adding, effectively 3 terabytes of data to this. And then hopefully the percent used is going to drop, right? Because now there's more capacity available, and this fake amount of data that we've used is far less as a percentage, right? Please work.
Question is, who's calling the AWS API to provision or
Right. So the framework. So that Mesos framework is the one that's actually calling the. Well, so for this particular software-based storage platform, that framework is tightly coupled with that application, this storage platform. So that framework is the one that actually recognizes, because it knows about this storage platform, it knows how to monitor that state. It knows that the storage pool is approaching full, right? Because this framework and this application are tightly coupled together. And when it recognizes through the API calls of that storage framework that we're approaching full on this storage pool, it will go out, that framework will go out and make the AWS calls to create these EBS volumes. And because we can also, after those EBS volumes get created, because this framework is so tightly coupled with this application, the framework can tell this application, give it a kick in the butt and say, hey, by the way, you have 3 1 terabyte volumes that are now on, that have been connected to your AWS EC2 instances. Go and attach them to your storage pool. And thankfully enough, it has. It actually did work. So we have a whole bunch of extra capacity. The threshold hasn't changed because it's just an arbitrary threshold about create more volumes when, we're getting in trouble. And the amount of used data has now dropped to 14%. So by simulating kind of an oh my god, we're not going to make it kind of scenario, we're starting to approach full. And I don't know if you have any backup administrators or SAN people who are deal with SAN stuff. When you start to approach full, if you hit full, the world's just kind of crashing down. And so the idea of this talk is, hey, you have this ability to monitor your application. You take all this stuff up with your container scheduler, move it into the cloud. You now have the ability to change the environment from underneath you and effectively fix your application's problems. And I guess, we'll just go to questions there.
So if Mesos has this capability, what's the use of SCaLE?
Yeah.
Any node can provision this new storage if it's using Mesos, right?
So, right, but the framework installs and configures the storage platform on your Mesos nodes.
It's using SCaLE. Mesos uses SCaLE underneath the covers.
If you want persistent storage for an application, yes.
So then, back to my original question, which one is actually using the AWS API?
Yeah, so let's go back here.
Because you mentioned Mesos is actually doing that
AWS
API call, or is it
this
SCaLE?
Mesos framework, which is effectively, think of a Mesos framework as a specialized plugin for Mesos. It's a plugin that you create that has special knowledge about your application, and in this case, it's SCaLE. Does that make sense?
Okay, so Mesos is just using SCaLE, which internally in its framework.
So
No.
Mesos isn't using it. Well, it's using it in the sense that if you start a workload, if you start a container and you want to provision an external volume, Mesos under the covers will call RexRay. I know there's a bunch of stuff. Maybe we can talk about it offline, but Mesos will start the container, make the hooks to provision the SCaLE volume, and attach it to that container.
Okay, so you pointed to a lot of GitHub pages. you pointed to a lot of the GitHub pages. We don't have to pull down these different components.
No, so if
It all comes with Mesos.
no, it all comes with the SCaLE framework.
Oh, it comes with the SCaLE framework.
Yeah. So you deploy the SCaLE framework to Mesos. That thing installs and configures SCaLE and all those other glue applications in your cluster.
Okay.
So effectively, I curled that command that says launch this framework, and it under the covers took care of all that stuff for you. Like you didn't even have to be aware that Rexray was getting installed and all that stuff. I really just only had the UI up there so that for me I knew everything was okay, and so that you can see when we faked dumping a bunch of data into this storage pool for SCaLE, that we could visually see that that it's starting to fill up, and then when we provision the volumes, we can visually see that we have enough capacity now.
So it works when it's installed in the configure, but as someone that starts fresh, I'm going to have to install all this stuff and configure it. So I would have to install Mesos. I have to install SCaLE. I have to install.
Yeah. So Mesos, just like Kubernetes and just like Docker Swarm, those are container schedulers. So you need to have, in this case, Apache Mesos, this particular container scheduler to use this framework. Got a question in the back.
Yeah, so I just want to make sure I understand this. We're using Ceph right now. And so we have 300, 400, 500 Mesos slaves. Every one of these slaves running containers, and on every one of them, there are mounts from Ceph to make volumes available to Docker containers so that when they spin up, if they need that storage, they'll mount that storage in the container. So with this, if I'm understanding this correctly, the volumes that are available through SCaLE will be visible on these slaves without even looking at the containers?
Visible on the slave.
In other words, if you do a DF on a Mesos slave, you'll see the volumes.
Yes, but they're using, so in the case of like Docker or Mesos, right?
Right.
It's using, Yeah, it's only for mount. Yeah, only for mounted. So effectively, the whole idea of containerization is that when you have a particular workload and you have a volume for that workload, only that container can see that particular volume.
So you have a security layer.
Oh yes, most definitely.
Right.
Yeah,
so it has to be somehow some token or something that authorizes it to actually utilize the volume.
What's the underlying technology for? I can't remember the name of it. No, for Mesos containerizer, which Docker uses too. I forgot.
Right.
But they have.
I know what you're talking about.
Yeah, they have security built in such that if I have a particular container like a Postgres.
Right.
And you have another container that comes up that's Elasticsearch, you can't go mucking at each other's data, right?
No,
it's completely isolated.
Right.
Yeah.
Okay.
And so when you provision a volume for your workload, so if you want to provision a SCaLE volume for Postgres, for your Postgres database, only that particular Postgres instance will have access to that volume and can scribble data to that volume.
Okay. Okay, great. So you can have shared volumes in this or not? Because depends. We find that it depends. Like Ceph, some of the file systems allow shared volumes. Others, they have to be exclusive.
Yeah. So two caveats, right? One, it depends on the application, right? If you're going to share volume, you better make sure that volume or that those two particular applications can work well together, so they can read write to that same volume. And then two, the underlying storage platform also has to support the ability to share volumes.
Okay.
SCaLE does. But like I said, it just depends on your underlying application. So like as an example, right, for VMware, because I know VMware, and so if you need to create a data store, you create a data store out of LUN, and you have X number of ESX hosts that are there. You share that LUN between those ESX hosts, right? That's how vMotion works, right? But that underlying data store, your VMFS, is smart enough to know that we can share this particular volume or this LUN and yeah. Yeah. Any other questions? Oh, I actually filled the entire time. Thank you guys for showing up. I know you guys missed beer for me, so I do appreciate it.
I'm not aware of any malware that launches itself without actually booting something. The only people who've had that are staff and the other three presenters of the day. So. And we know who they are.
Yeah. Cool. Thank you. I hope you enjoyed it. Sorry, I was talking. Sorry. It's all yeah. SCaLE is free, but it's not open source. So one of the reasons I purposely tried to minimize SCaLE is because it's not open source. Technically, there's no reason why you couldn't do this for any software stuff. So I just happen to use SCaLE because I'm familiar with it and I understand it. But well, it's free. I mean, you only pay if you want support for it. Yeah. So, but you technically could do this with any other software. So if you wanted to do something like this for like NFS, you could do it. I wouldn't do it, but I'm just saying you could do it. Right?
Yeah, I moved away from posting our own stuff on my storage because it's like self-contained applications.
Right.
Yeah, we kind of moving away from that. I hope it's
right.
My else is the available amount of data we started with like that.
It was, I think it's,
It's 5 something. Yeah. So is that like an online store or what? Where is that coming from?
so that came, so initially, SCaLE platform, I needed to have some initial storage there, right? To connect to that platform. And then I also needed to have that storage to fill up data for like provision more boxes.
That was also.
Yeah.
So the entire storage pool.
Yeah. The underlying physical as in what the data was. Yeah, it would go to machine.
So I was thinking like, was it really kind of like structured?
Yeah, so SCaLE is the storage platform. It strikes the data across all three so that if you have a node box, you can have all the data.
An easy way to look at this is AWS is very easy to start, right? Like, 99% of the time, you're never going to have AWS, right? You're running your own data center internally. But this is just a way to be able to show you like how to scale, right?
So one question I have is that you built it into that how does that ensure consistency in I want to data to be snapshot? How do you make sure that when I take a snapshot, because obviously we always allow snapshot page.
Don't think in regard to that. We're talking like two different layers, right? So like SCaLE manages its own layer of data, like EBS is like another layer. EBS at this point is just a foundation. Like don't even think about EBS as existing here. Just think of it as just raw spinning. It's a backend server full of hard drives. Yeah,
And if you wanted to create a snapshot, you actually create a snapshot on SCaLE.
Yeah, and then you would use whatever backup technologies to interact with SCaLE to be able to take it off elsewhere or whatever you need.
And it also handled by
Yeah, so if you lose a drive for whatever reason, or you lose the entire network, something happens. If you have other nodes there, any data that was missing from that particular node failure gets revamped. It's not something you have to finish, which was yet another appealing reason for you.
I guess I'm just curious about how it works.
In the real world, like not with AWS or what?
Yeah, how it works through the software defined. How does that more so than
I'm not I don't work on SCaLE. Internally, they have this user soft analysis that does the rebalances and stuff.
And even that can happen not just when you have node failure, but when you add nodes, it rebalances across those new nodes too, right?
So we have node failure, does that mean for you to recover service, you have to already have a top standby node that, that's ready to...
Quickly, to just kind of go over the architecture of SCaLE, you have these components that are installed and everything. You have the SDS, an NPM, and an SCC. So you have the NPM, which is the metadata managers, and essentially those are like your kind of what you consider like cluster managers, right? Like that's your API gateway access. So you have like 2 or 3 of those, and then you have racks of pizza boxes, and each one of those has an SDS installed, and then those basically like form the cluster host, right? And then you have an SCC, which is a controller. You install those on each one of the hosts that make you run a container, how you actually access the volumes, right? So essentially, you can have a whole piece of a rack of pizza boxes that function nothing but storage. Like you've got very little pizza, a ton of storage. Then you got another rack of pizza boxes that are your compute nodes. And each one of these have an SCC, and then they can consume storage from here. Or you can have basically compute and storage at one of the boxes. SCC, SDS, and SCC, and NPM, you can call it compute, but SDS and SCC, you can call it all of them. And then so